Hello students. Why NAND and NOR gates are called as universal gates? Let us see the answer of this question in this video. You can see you have already identified different types of gates, out of which the second type we have written down as a universal gates, which are NAND and NOR gates. So why they are universal gates? Let us see. You have already identified there are three basic types of gates, that is AND, OR and NOT. Now with the help of NAND gate only, we can easily construct the operation and the logic of AND gate or OR gate or NOT gate. So therefore, simply NAND gate is sufficient to create the logical expression of basic gates, that is NAND gates, NOR gate and NOT gate. Similarly, NOR gate is also sufficient and enough to create the logic of AND gate, OR gate or NOT gate. So therefore, these two gates, that is NAND gate or NOR gate, simply they are responsible or they are easily used to create the different types of basic gates, that is AND gate, OR gate and NOR gate. And then with the help of combinations of AND OR and 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 NOT, you can find different types of gates, but the basic gates can be constructed with the help of NAND and or NOR gates alone. That is the reason why they are called as universal gates. What do you mean by universal gates? They can obviously use simply to construct different types of gates, right? So therefore they are called as universal gates, right? So therefore let us see how a single NAND gate or only NAND gate can be used to construct different types of basic operations and or and not. Here I have already shown you the truth table of a NAND gate having two inputs A and B. These two inputs are going to create four different combinations 0, 0, 0, 1, 1, 0 and 1, 1. And along with it, in the output column, you can see its output for the respective combinations. So therefore, let us see how NAND gate can be used to create a NOT gate. Here you can see a single NAND gate is used. This single NAND gate has usually has got two inputs, but now we are going to use this single NAND gate and its input, right? So therefore, let us use black color. So the two inputs, instead of two inputs, only one input we are going to use, and that input is A. So therefore, the two NAND gates two inputs are A and A only, right? So this is what entered into the system of NAND gate. Now when you consider NAND gates, then it has got these four different combinations. So out of this, if I consider A is equal to say 0, then this A will be obviously 0. That means this NAND gate is going to receive the inputs as 0 and 0. Now if a NAND gate receives input 0 and 0, then the output will be obviously 1, right? So therefore, in this case, you are going to get the output as 1. And this output 1 is nothing but, you realize that it is a complement of 0, which is A complement, right? A was entered as a 0, right? So this is what happens when you consider A is equal to 0. And what you are going to get is A complement. Similarly, if you consider A is equal to 1 as an input, right? Input can have two states only, 1 or 0. So therefore, instead of 0, let us consider another input, right? Say 1. So therefore, instead of 0, I'm going to use another input, say 1. Now when I entered 1 over here, that means this second input is also obviously 1. Now once you enter these two inputs, then you realize that you are talking about this combination 1 1, then output is 0, right? So therefore at the output side you are going to get 0, but 0 is nothing but complement of 1, and which is enter at the input, so you are again going to get A complement. So therefore this is nothing but a NOT logic. A is entered and you are going to get in both cases A complement at the output. So one input, one output, which is nothing but property of a NOT gate, right? So therefore NAND in this way can be used as a NOT gate. But for that case, this kind of connections has to be made, right? Now let us see how next diagram for NAND gate can be used. Now here you can see NAND gate can be used as a AND gate. Now for that case you require two NAND gates connected in this fashion. First, NAND gate is connected having inputs A and B. The output of NAND gate is obviously A dot B complement, which is written down here. Now this A dot B complement is given as an input to this combination, and this combination is nothing but this, right? This is nothing but, right, NOT gate. And if AB complement is entered as an input to NOT gate, then NOT is going to apply another complement on it. So therefore, this will become A dot B complement and upper or a complement of this due to this NOT gate, right? Why? Because this is what the NOT gates diagram. And this NAND gate simply acts as a NOT gate. So whatever input that are entered in this particular diagram will be complemented, and the complement of A dot B will be obviously complement gets cancel each other, and you get A dot B as a simple output. And in this way, NAND gate, these two NAND gates are used to create a AND gate logic. And final one, how you are going to use NAND gates only to create a final OR gate output. Here three NAND gates are used and they are connected in this fashion. Here A and B are connected separately to two different NAND gates. So, and you realize that this whole diagram where A is connected is nothing but representing NOT gate, right? This is NOT gate, right? Right? So therefore, whatever input A will be complemented at the output. So therefore, A will be complemented as output as A complement, and B will be complemented as a B complement. So therefore, these two will now act as a inputs to this third NAND gate, which is connected at the outputs of these two NAND gates. So therefore, this NAND gate receives input as A complement and another as a B complement. So because of this connection, now you realize that this NAND gate receives A complement as a one input and B complement as another input. So this particular situation is going to give you output as a OR gate. That is Y is equal to A plus B. How? Let us see. The NAND gates operation is like this. Whenever you enter two inputs as A and B to the NAND gate, then output will be A dot B complement. So therefore here the two inputs, so therefore if two inputs are there, A dot B, but these two inputs are complement, right? A complement and B complement. So therefore A complement dot B complement and its complement. Now when this type of situation is present, then here the this outer complement sign is going to change the sign, or is going to perform negation on individual elements, as well as the operation between the two elements also going to be changed. So therefore dot will be replaced by plus, that is OR, that is AND will be replaced by OR, and A complement will be replaced by A, and B complement will be replaced by B because of this complement sign. So therefore now the output is A plus B, which is nothing but a OR gate. So in this way, NAND gate simply alone can be used to create the logic of NOT gate, AND gate and OR gate, right? So therefore NAND gate is called as universal gate. Similarly, there is a NOR gate also, which is called as a universal gate. So let us see in the same fashion how NOR can be used to create the logic of NOT, OR and AND, right? Here simply putting the truth table, this truth table is meant for two input NOR gate, and the outputs are different input combinations are 0 0 0 1 1 0 and 1 1. These four combinations are going to create four different outputs. These are 1 1 1 0 because of basic terminologies of a NOR gate. So in this case we will see how this NOR gate can be used. Single NOR gates or multiple NOR gates can be used to create the different logics. You can see here in the diagram, the NOR gate is connected and the single NOR gate is present. Now this single NOR gate is responsible for creating the output as a inverted one. So here the input A is present at the input side, but this single input will be given to both inputs of a NOR gate. This NOR gate is having two inputs, but both inputs are being given as a only. So therefore this is also A and this is also A, right? So therefore let us change the ink color a little bit, right? Let's see, black color. Okay, so therefore this is A and this is A, and you realize that A can have two states. Either A can be 0 or either A can be 0, right? So if this A is equal to 0, then this will be also equal to 0. So when 0 and 0 enter as inputs to NOR gate, then the combination of 0 0 gives you output as a 1. So therefore at the output terminal of this NOR gate you will get 1, and this 1 is nothing but a complement of 0. And 0 is what? 0 is given as an input, so therefore you are going to get output as a complement, right? So therefore you are going to get output as a complement when 0 0 is given as an input to the NOR gate, right? So therefore this is about when the inputs are 0. Now let us see other inputs. First of all, let me erase all those things. Okay, so now let us consider second second type of input, that is when A is equal to 1. So when A is equal to 1 is going to be entered into the system, then both inputs will be 1 1. Then you realize the combination that I am talking about is this 1 1, then output will be 0. This 0 output is nothing but 1 complement, and 1 complement means it is actually complement of A. So therefore you realize that whenever input is given as 1 or 0, the output will be exactly complement of it, and which is nothing but a property of NOT gate. And therefore here you can see NOR gate can be simply used as a NOT gate by connecting both inputs to single input only. In the previous case also, in the case of NAND gate also, NAND gate works as a NOT gate when you connect both inputs to single input only, then that connection will be obviously NOT gate. So here also NOT gate configuration of a NOR gate. Then second one, in the beginning we are connecting a NOR gate, and this NOR gate will be attached by another NOR gate also. So let us see, first of all, this NOR gate is present, and this NOR gate has got two inputs A and B. Then the output of this NOR gate will be, as you have seen, it will be A plus B, complement of A plus B, right? So therefore this will be A plus B and its complement of A plus B. Now this complement of A plus B will be given as an input to another NOR gate which is connected in this fashion. Now you can see that this diagram, second diagram, is nothing but NOT gate, right? This NOR gate connected in this fashion acts as a NOT gate, which we have seen in the previous example. So therefore whatever input present at this will be complemented at the output side. So therefore if a complement of A plus B is present at the input of NOT gate, then the output will be complement of A plus B. And two complements if applied on a same number, then the output will be obviously A plus B alone, because these two complements are going to cancel each other. So therefore output will be simply OR gate. So this diagram tells you how NOR gate can be used to construct the logic of OR gate, right? Next one is NOR gate constructed to create a logic of AND gate. And this is same diagram which we have seen in the case of NAND gate. Here, 3 NOR gates are implemented. The first 2 NOR gates are going to receive the signals A and B separately. So therefore, you realize that this combination of NOR gate is nothing but a NOT gate, right? So therefore, whatever input present at A will be complemented at the output, right? Similarly, this also, this connection is nothing but NOT gate. So therefore, whatever connection made at the input will be complemented at the output. So therefore, A complement and B complement will be considered as inputs to this NOR gate. And the NOR gate's logic is whatever connected at the inputs will be ORed and it's complemented. So therefore, here you can see A complement, B complement, the output will be AND gate. Now how this has been created, you can see first of all, when the inputs are A and B, the output of NOR gate is A plus B and its complement. So if input is A complement and B complement, then output will be obviously complement of A complement plus B complement, right? The complement of A complement and B complement. Then when there is a complement, that is when there is a negation outside any particular logic, then this negation is going to change the operations between any two logics. So therefore here this plus, that is a OR gate, will be replaced by dot, that is AND gate, and A complement is replaced by A and B complement is replaced by B because of this complement sign. So therefore the output will be A dot B, and therefore this works as a AND gate. So therefore these two inputs given at this combination, which is a combination of different NOR gates, the output will be A dot B. So this is working of NOR gate as a AND gate. So here also simply NOR gate can be used to create 3 different logics, NOT, OR and AND. Therefore these basic gates once created, they are going to create different logics obviously, but the basic gates can be created simply by using NAND gate and NOR gate. Therefore these two gates are called as universal gates.